Welcome to AI for Specialists. Imagine if you're a mechanical engineer cutting weeks, maybe even months off your design cycle. And not by just, working longer hours, but by completely rethinking how you approach design. That's really the huge shift artificial intelligence is bringing to mechanical product development. It's enabling something that honestly used to sound a bit like science fiction, a genuine first-time right approach.
Exactly. And what's so key here, what's really transformative, is that AI isn't about replacing engineers at all. It's acting as this incredibly powerful augmentation. It shifts your role, you see, from being, let's say, a tool operator, someone focused on the CAD software clicks, to becoming more of a system architect, someone tackling the big, complex challenges. And the outcome, drastically reducing those traditional inefficiencies, the endless iterations that plague product development.
Right. And the sources that we've looked at for this deep dive, they really map out this new way of working. It covers everything from the very beginning, the initial idea, all the way through detailed design, sophisticated simulation, and even direct automation of tasks. So today we're going to highlight some specific technologies and talk about their real measurable impact. Let's really unpack how this changes your day-to-day. We all know the feeling, right? That conceptual design phase can be such a grind, so much time buried under just, manual research. I remember spending days, literally days, just sifting through patent databases, technical papers, trying to find relevant information, drowning in PDFs. That's the kind of bottleneck we're talking about eliminating, isn't it?
Oh, absolutely. A huge time sink. And that's precisely where large language models, LLMs, like ChatGPT, Gemini, others, really come into their own. Think of them as knowledge co-pilots. They can synthesize just vast amounts of unstructured data. We're talking patents, academic journals, competitor analyses. Maybe you need to know what Boston Dynamics or ABB or Fanuc are up to, or even complex material selection, say, for a harsh marine environment. And they do this in seconds, giving you a really informed starting point, much faster than doing it manually.
Okay, knowledge co-pilots, I like that. But there's a catch, right? We hear about AI hallucinations. For an engineer designing something physical, something that has to bear load or withstand pressure, a hallucination isn't just wrong, it could be dangerous.
That is the crucial caveat, absolutely critical. You, the human expert, must rigorously validate the output from these LLMs. Because yes, they can hallucinate, meaning they can generate plausible sounding, but factually incorrect or nonsensical information.
So how does that validation work in practice? If I still have to check everything, am I really saving time? What's the overhead?
It's less about checking everything from scratch and more about directed verification. Think of it like debugging code. The LLM does the heavy lifting of finding and synthesizing potential information, maybe surfaces connections you wouldn't have seen. Then you, with your domain expertise, apply filters. You ask critical questions. You cross-reference the key claims. You refine it. It becomes an iterative loop. The LLM accelerates the initial broad search, but human expertise remains firmly in control of accuracy and application. So yes, it still saves significant time overall.
Okay, that makes sense. It's an accelerator, not an oracle. So LLMs help us synthesize knowledge faster. But what about the actual design geometry? Traditionally, let's be honest, designs are often constrained by an engineer's own experience, maybe the company's past projects. We tend to design variations of what we already know.
Exactly. And you start asking, what if we could break free from that? What if we could invert the process entirely? And that's really the promise of technologies like generative design or GD and topology optimization, TO. Instead of starting with the shape and refining it, you start with the fundamentals. You define the functional requirements. Where are the loads? What are the keep-out zones? What material properties are needed? What are the constraints? And then the AI explores literally thousands, sometimes millions of design possibilities within those boundaries. It generates optimized geometries, often forms that look quite novel, very organic, things a human might not sketch.
Right, these very fluid, almost skeletal structures sometimes.
Precisely. And there's a subtle difference people often ask about. Generative design is often thought of as additive. It sort of grows the material where it's needed most, like for additive manufacturing. Topology optimization is more subtractive. It starts with a larger block of material and carves away everything that isn't strictly necessary to meet the performance criteria. Both aim for optimal material usage.
Those novel organic geometries sound fascinating from a pure engineering perspective. But I can almost hear the skepticism from experienced engineers. Okay, looks cool, but how on earth do I make that? Is it practical? Are companies actually implementing this successfully? What are the real-world benefits?
Oh, definitely. It's moved well beyond the theoretical stage. There are some really compelling examples. Take General Motors. They used generative design on a seat bracket assembly, a fairly mundane part, you might think. They went from an assembly of 8 different parts down to a single complex component. The result, a 40% weight reduction, and crucially, a 20% increase in strength. Think about that.
Wow, 40% lighter and stronger, and from 8 parts to 1?
Exactly. Think about the ripple effects. Fewer parts means simpler assembly, reduced inventory, streamlined supply chain, fewer points of failure.
The downstream benefits must be huge.
They really are. And it's not just automotive. Honda used topology optimization for a critical engine component, the crankshaft. They achieved a, frankly, staggering 50% weight reduction on a crankshaft. That's immense for engine performance and efficiency.
50% on a crankshaft. That's incredible. So this really does shift the engineer's focus, doesn't it? You're less concerned with manually drawing every fillet and radius and more focused on defining the problem correctly, setting up the right constraints, understanding the system interactions.
That's it, precisely. You become less of a geometric modeler and more of a systems thinker, a problem architect. You define the what and the why, and the AI helps explore the how.
Okay, so better ideation, better geometry generation.
Yeah.
What about another classic bottleneck? Simulation. Things like finite element analysis, FEA for structural checks, or computational fluid dynamics, CFD for fluid flow. Historically, that happened late in the game. You'd finish the detailed design, hand it off to the simulation specialist, wait days or weeks, and then maybe find out you needed a major redesign. Very costly.
A huge pain point. Simulation was often a validation step, not a design tool, because it was so computationally expensive and time-consuming. But this is another area where AI is making massive inroads with AI-accelerated simulation. The core idea is using what are called surrogate models. These are AI models trained on vast amounts of high-fidelity simulation data. Once trained, these surrogate models can predict performance stress, deformation, fluid flow, whatever it is, in near real time, or at least orders of magnitude faster than traditional solvers.
Near real time. So I could tweak a parameter in my design and see the likely performance impact almost instantly.
Pretty much, yes. It effectively democratizes analysis. You don't have to be a deep simulation expert or wait days for results. The design engineer get immediate feedback right within their workflow. Think about Faurecia, the automotive seating manufacturer. They reported reducing analysis time by an astounding 93% for complex vehicle seating crash simulations using AI methods.
93%. That's not just faster. That fundamentally changes how you design.
Right.
It encourages experimentation.
Absolutely. It fosters what you might call an experimentation-positive mindset.
Yeah.
You can explore dozens of what-if scenarios, different materials, different geometries, quickly and easily because the feedback loop is so tight. It integrates simulation much earlier and more often into the design process.
Okay, this is powerful stuff. Now, what about the latest wave? I'm hearing more about LLMs, those same language models we talked about for knowledge synthesis, actually automating CAD tasks directly.
Yes, this is perhaps one of the most exciting frontiers right now. It's about interacting with your design tools using natural language, moving away from needing dedicated programming specialists or engineers, learning complex scripting languages for automation.
So instead of writing code, I can just tell the CAD system what I want it to do.
In essence, yes. You can describe complex or repetitive tasks in plain English, and the LLM can translate that description into executable code for the MCAD software's API, the application programming interface. Think about practical examples. Maybe you need mass customization. You have a spreadsheet, a CSV file with hundreds of variations of parameters for a product. You could instruct the LLM, update the parametric model using the values in this file, and export each configuration as a step file.
Wow, okay, that would save hours, maybe days of manual work.
Easily. Or automating bill of materials creation based on specific criteria.
Yeah.
Or batch modifying custom properties across thousands of parts in a large assembly. Tasks that are tedious, error-prone, but necessary. Now, it's not magic. It's often an iterative process. You give the instruction, the LLM generates code, you test it, maybe it needs debugging. It's a human-in-the-loop process. But the potential to automate bespoke workflows without deep programming skills is immense.
And the really big aha moment here, I think, is capturing knowledge. So much valuable expertise, especially from senior engineers, is often just tribal knowledge, right? It's in their heads based on years of experience. How they approach certain problems, shortcuts they use.
Exactly. It's hard to document, hard to transfer.
But with this LLM-driven automation, you're essentially capturing that expert workflow, that logic, and turning it into a reusable automated tool. You're taking that tribal knowledge and making it an executable asset for the entire team, the whole organization. It really democratizes expertise at scale.
That's a fantastic way to put it. It really scales expertise. And all of this points towards an evolution in the skill set engineers need. It's less about just the mechanics of the tool and more about systems thinking, becoming comfortable with data, understanding data literacy, learning prompt engineering, how to effectively communicate your intent to the AI, and critically, combining that deep domain expertise you already have with AI proficiency, which leads back to the earlier point. AI won't replace engineers, but it will replace engineers who insist on working like computers, doing repetitive tasks that AI can automate.
It really reframes the value proposition of the engineer, which leaves us with maybe a provocative thought for you, the listener. Human creativity, our intuition, that spark, it often thrives in what you might call the entropy gap, that messy, uncertain space where problems aren't clearly defined, where we need to frame the challenge in a novel way before we even start looking for solutions.
The ability to ask the right questions.
Exactly. AI, especially the kind we've discussed today, excels at optimization within a defined solution space. Once the problem is framed, AI can explore possibilities and find optimal solutions at incredible speed. So the future isn't human versus machine. It's human and machine, a really powerful symbiotic relationship. The human engineer provides the creative insight, the context, the framing of the problem.
The crucial why.
The why, precisely.
Yeah.
And the AI provides the computational power to rapidly explore, analyze, optimize, and automate within that framework.
And that synergy, that combination, ensures the continued, and I'd argue elevated, relevance of the mechanical engineer in this new era.
Well said. It's about working smarter, augmented by these powerful tools.
Well, that's all the time we have today. Until next time on AI for Specialists.